when we talk about ways of expressing equilibrium constants, first we have to decide, are we dealing with a homogeneous equilibria or a heterogeneous equilibria? We talk about homogeneous equilibria, the reactants and the products are in the gas phase or the aqueous phase. So that's what it means that for all reacting species to be in the same phase. They're in the gas phase or the aqueous phase. So when you're in the gas phase, you can be expressed as a Kp expression, meaning the uh, pressures of the products over the pressures of the reactants raise their stoichiometric coefficients, or the concentrations of the products raise their stoichiometric coefficients divided by the reactants raise their stoichiometric coefficients. When you're in the solution phase, when you're in the solution phase, it's strictly moles per liter. I mean, that's the concentration unit we're using. All right. So, for example, dinitrogen tetroxide again, right? Reacting to form nitrogen dioxide. So, products over reactants raise their stoichiometric coefficients. So, if we're talking about a Kc expression, meaning an equilibrium constant expressed in terms of moles per liter, concentration of NO2 raised to the second power divided by the concentration of NO4 raised to the first power. If we're talking about pressures, we can put pressures up in the numerator or the denominator, and we get a Kp expression. So they'd be different values because we're using a different unit, but they'd represent the same thing. How far forward the reaction goes when the reaction stops. All right, so equilibrium concentrations for carbon monoxide reacting with chlorine to form CoCl2. We're given the equilibrium concentrations, and we're kind of going backwards here, right? What is the equilibrium constant when these are the equilibrium concentrations? So just plug them in. Plug them into products over reactants, raise their stoichiometric coefficients, and solve. Okay, so hey, we got a Kc value bigger than 1, so this is a spontaneous reaction. I'm making a lot of products, losing a lot of reactants. The Kp value for the reaction is 158. Calculate the pressure of oxygen when we know what the equilibrium pressures are for the other two. So in this situation, you're plugging in the known pressures, setting them equal to the Kp value, and solving for the missing pressure, right, the oxygen pressure. So multiply by both sides by 0.4 squared, divide both sides by 0.27 squared, and solve. So Kp is used to find the missing pressure. All right, so there's a relationship between these two constants, right? I mean, as remember, gases are expressed as pressures, and we can talk about moles per liter of gas, right? So moles of gas divided by liters of gas. So the relationship derives out in terms of Kp and Kc is Kp is equal to Kc multiplied by RT, gas constant, temperature in Kelvin, raised to delta N. So what is delta N? Delta N is defined as the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. So it's a very specific thing. So we sum up the coefficients of the products, subtract the coefficients of the reactants, and we get delta N. All right, so solution phase, like I said before, right, the concentration term is always moles per liter. Important to understand that only things in solution or things in the gas phase are expressed. Liquids are not expressed in equilibrium expressions, right? So solids and liquids are left out. So if I'm writing the Kc expression for this reaction, my dog's bugging me again. I'm going to write the Kc value for this expression. I leave water out of the Kc expression. Got get out of here. Oh, sorry, I'm back. So Kc is going to be equal to the concentration of the acetate ion times the concentration of the hydronium ion divided by the concentration of acetic acid. We leave water out of the expression. All right, so as we said just a minute ago, only aqueous things and gases can appear in equilibrium expressions. We don't put solids or liquid terms in the expression. So when we talk about heterogeneous equilibria, we're dealing with a solid interface. Something like calcium carbonate turning into calcium oxide solid and carbon dioxide gas. So when we talk about the Kc value, it's strictly based on the concentration of the carbon dioxide gas. The solids don't appear. And the reason for this is they have no impact on the position of equilibrium. If I grind them up, right, increase the surface area so that I speed up the rate of calcium carbonate turning into carbon dioxide, I also speed up the reverse reaction. So increasing the surface area of the or adding more solid, right, getting more in there, getting a greater surface area, doesn't shift the reaction forward. All right, it just increases the reaction rate in both directions. Same with adding more calcium oxide. It doesn't shift the reaction backwards. It just increases the rate going backwards and forwards. So the only thing that has an effect on position of equilibrium is the pressure or the concentration of the carbon dioxide gas. All right, so practice exercise. What is the Kc and Kp expression for the reaction shown? So we've got nickel solid reacting with 4 moles of carbon monoxide to make nickel, whatever that is, CO for them in the gas phase. I don't know what that is. What is that? Hypocarbonite, I guess. Nickel hypocarbonite gas. Okay. So, hey, the gases only appear. You'll leave the solid out. So product sum of reactants raised the stoichiometric coefficients. It's the concentration of the product raised to the first power divided by the concentration of carbon monoxide raised to the fourth power. Same for the Kp expression, except we use pressures instead of concentration units. By the way, guys, this is what the brackets represent. I don't know if we explained this before, but the brackets around the formula represent moles per liter. So write a little note. The brackets represent moles per liter. What is the value for Kc and Kp for the equilibrium shown? So the solid doesn't appear. So we look at the pressure of the ammonia gas and the dihydrogen sulfide gas. We plug them into the Kp expression, right? So atmospheres times atmospheres. I end up with Kp being equal to 0.0702. Notice, guys, there is no unit for for equilibrium expressions. Whereas with rate constants, we had units to consider. There are no units for equilibrium expressions. They're unitless. So this is the Kp value. If I want to get the Kc value, I can plug into that equation, right? Kp is equal to Kc times RT raised to the delta N. So they gave us a temperature, 295. R is R. The question is, what is delta N in this case? Well, I have no gaseous reactants, so that's the sum of the gaseous products minus the sum of the gaseous reactants. So I've got 1 plus 1, because that's the coefficient for the products, minus 1 gives me, minus 0 gives me 2. So plug in R, plug in T, raise it to the second power, representing delta N, along with Kp, Kp, and solve for Kc. So multiply both sides, or divide both sides by RT raised to the delta N, and we solve. We get a Kc value. All right, with multiple equilibria, if a reaction can be expressed with the sum of 2 or more individual reactions, the equilibrium constants for the overall reaction are the product of the individual equilibrium K values. So if I know what the K values are for taking the first H off of hydrosulfuric acid and the K value for taking the second H off of hydrogen sulfide, and I want to know what the K value is for taking both the H's off, I'd add the equilibria together to get the overall equation, and that means I multiply the K values. So if I added these equilibria together, I would cancel hydrogen sulfide and then end up with 2 moles of H plus and 1 mole of sulfide. And I'd multiply the K values. So multiply the K values and get the overall K value. So a very non-spontaneous reaction, right? It's a weak acid, so the first H coming off is little. The second H coming off is even more pathetic. If you multiply them together, taking both H's off is very unlikely, right? So 10 to the minus 27. That's how hard it is to take both of those H's off of dihydrogen, or have both those H's float off in water. Nothing. All right, the form of K and the equilibrium equation. All right, when the equation is reversible, written in the opposite direction, the equilibrium constant becomes the reciprocal of the original equilibrium constant. So if I get a K value going forward, and I turn the reaction around, I want to know what the K value is for the reverse reaction, I divide it into 1. K value also depends on how the equilibrium expression is balanced, right? So with different coefficients, you're going to get a different value for K, which I always found odd, but that's the way it is. So Kc value at 375 degrees Celsius for the formation of 2 moles of ammonia. If I want to turn this around, right, take ammonia apart, turn it back into nitrogen and hydrogen, the K value would be the reciprocal of 1.2. So I divide 1.2 into 1, and I'd get the K value go in the reverse direction. So hey, it's balanced differently, right? So we're making 2 moles of ammonia in the first equation. We're only making 1 mole of ammonia in the second equation. So when I plug these values in, I'm essentially getting the equilibrium expression to the 1/2 power. So if I took the K value for 2 moles and took it to the 1/2 power, I get what the equilibrium K value is for only getting 1 mole. So it's different. What is Kp for this reaction? Okay, so we're using that equation again. I've got 4 moles of gaseous reactants, 2 moles of gaseous products, so 2 minus 4 gives me a minus 2. So yes, you can raise RT to a negative exponent, right, to the negative 2 power. So plug in R, plug in T, multiply it by Kc, and get Kp. All right, so summarizing. Concentration of the reacting species are always in moles per liter, so we don't use any other concentration unit. And the brackets in the law of mass action represent moles per liter. If we have a Kc expression and we want to know what the Kp value is, we can plug into this conversion factor to go from Kp to Kc or Kp to Kc. Concentrations of solids and liquids are left out, along with solvents. Equilibrium constants do not have units. All right, it's a unitless value. And the balanced equation counts. All right, so when you write an equilibrium expression, you have to write the balanced equation to show what equilibrium expression you're talking about. If a reaction can be expressed as the result of 2 individual reactions added together, the overall K value is the product of the 2 equilibrium constants. If we if we turn the reaction around, got a K value going in the forward direction, the K value for the reverse reaction is reciprocal. So divide it into 1.